Okay, so what have you been manipulating as integral for the moment? It's called the Riemann integral, the one that was theorized completely in 1854 by Bernhard Riemann. Okay, so the idea is that you can define the integral as some sum of rectangles. So you remember the idea, you discretize your domain of integration and you build some rectangles, so you can take the biggest value, the lower value, some mean value, but the idea is that you know how to make sum of rectangles, and that's going to approximate the area below your curve, right? So this is it. And we define the integral as the limit as the discretization step, so that size goes to 0, of that sum. Right. And all right. So and so we have decided that this integral sign, this one, comes actually as a big S, like the discrete sum becomes a continuous sum. So that's giving you the integral sign. And the dx is when the discretization step goes to 0 to some infinitesimal value dx. So you've got this animation that comes from Wikipedia, this one, that shows you how we are getting a better and better approximation of the area below the curve as the number of the discretization step becomes smaller and smaller. All right, so this seems a pretty nice way to calculate this area. But the question that arose then was, but okay, that's good, but what's happening when the function is not regular? Can we still do that? The problem is that it's okay to do take some small discretization size, but if your function does some very funky things and is not regular at all, it's not the convergence of this discrete series into a continuous sum is not very clear. Okay, so that's why there was a need at least to clarify this setting. So we want to know the regularity conditions under which we can do something that is going to calculate an approximation of the area. And also, we will want to be able to answer some general questions like the limit of given a sequence of functions, fn of t, right? So you've got a function that depends on t and on n. You've got an example here, right? Here we are defining a function that is going to have some constant height on some interval that is going to decrease. So we're going to talk about that in a minute, right? We want to know whether the limit of the integral of the limit in n of those integrals is the same thing as if you would calculate the integral of the limit as n tends to infinity of this thing. So that's one of the questions we want to answer, and we will see some kind of counter example. And the other kind of question is if I've got a function that depends on two variables, and if we integrate with respect, so for instance, this one, x exponential e minus x times t, and if I want to integrate only with respect to one of the variables, what's happening? Is it continuous? Do I get something that is continuous? Do I get something that is differentiable? And in such case, do we have that the derivative of the integral is the same thing as the integral of the derivative? Okay, so let's talk about these examples. First example, this sequence of functions. So fn of x is equal to n over 2 for x between -1 over n, 1 over n. So what does it look like? Let's take n is equal to 1, so for n greater or equal to 1. If n is equal to 1, that function is going to be, well, it's going to be 0 up to -1, 0 above +1, and in between it's going to be 1 over 2. 1 over 2n, n over 2, sorry, that's 1 over 2. All right, so that would be f1 of x. All right, the good thing, what is the area below this curve. Obviously, it's going to be 1 over 2 times 2, so this area is 1, and if you do the calculation, you're going to have that the integral of fn of x dx on R. We can do the integral on R because between negative infinity and negative 1 and plus 1 and plus infinity, it's equal to 0, so it's the same thing as doing the integral between negative 1 and 1 of constant value 1 over 2, and of course, this is going to be equal to if you do f2 of x, f2, so that's going to be the one that's worth 1 if x is between minus 1 over 2 and 1 over 2. So I'm here, and the value is 1. Okay, so basically what's happening, we're decreasing by half the width of the support of the function where it's non-zero, and we're increasing by 2, we're multiplying by 2 the height of the function, right? So guess what? If you're calculating this area, you can do the integral, or you can calculate it directly. You will get that the integral of f2 of x is again equal to 1. Okay, maybe you probably get to see where I'm getting to. If I'm doing f3 of x, it's going to be 1 if, it's going to be 3 over 2 if x is between minus 1 over 3, minus 1 over 3, 1 over 3, and so I'm going to get something like this. So I'm not exactly decreasing by 2, but well, it's something very similar. In any case, you have that this area is still going to be equal to 1. So what we obtain is actually that whatever the n, the integral of fn of x dx on R, you can sum it up as being the integral between minus 1 over n plus 1 over n of n over 2, of the constant value n over 2, and that's going to be 1. So actually, this sequence of functions has constant integral. Okay, so what is clear is that the limit as n tends to infinity of this integral is going to be 1 because for all n, that integral is equal to 1, right? My problem is that now if I'm looking at the limit, so you see we are decreasing the support of the function, so the support is where it's non-zero. We are decreasing it by 1 over n, 1 over n, 1 over 3, 1 over 4, etc., etc. And so the support of the function is going to tend to 0, of course, on both sides. So my interval negative 1 over n plus 1 over n, that's going to tend to a single value 0. And meanwhile, the value of the function, n over 2, that's going to tend to plus infinity. So in the end, at the limit, I've got something that is not really a function, that is actually called a distribution. We're not studying that this year, but it used to be part of the engineering studies a few years ago, which is 0 everywhere, except at 0, and plus infinity at 0, and some plus infinity value at 0. So actually, there is a way to represent it. It's just to make some kind of vertical arrow at 0. So that's not really a function. That's a generalized function. It's called a distribution, and that's called the Dirac distribution. That's just for your general culture. But the interesting thing is that if you consider the Dirac distribution, if you consider this thing, if you want to make the integral of the limit of fn of x dx, you can absolutely see this as the integral, okay, between minus infinity and plus infinity. Of course, I can split that Charles relation, this integral between minus infinity and 0 plus the integral between 0 and plus infinity. And the thing is that on both sides, that limit is going to be 0. Okay, the only place where the value of the limit function is not 0, it's at 0. And, so it has no kind of width. So what we have is that this is equal to 0. So what do we have in the end? We really have something quite surprising, that in that case, the limit of the integral is different from the integral of the limit. So what Lebesgue is doing is presenting some necessity for the functions in order to get or not this kind of equality. All right. So in order to maybe prevent this kind of thing from happening, or know it beforehand that this kind of behavior may happen. Okay, so this is the kind of case that couldn't be resolved using the Riemann integral. So that's why we need a new theory of integration. And then what else do we have? Okay, do we have this kind of thing? So this, let's have a quick look also at this other example. So this other example, I want to integrate between 0 and plus infinity. No, that's not the one. So the correct second example is that one. Let's define a function, capital F of x, such that the integral between 0 and plus infinity, it's defined by being the integral of between 0 and plus infinity of a function f of x t of two variables, which is x exponential minus xt. And I will integrate with respect to t, so that in the end, the t variable is going to disappear, and I will be left with only the x variable. That's why it's making a function of x. All right. What do we see? We see that f at 0 is equal to 0. Why? Simply because if x is equal to 0, that's I'm integrating the 0 function, and so we get the integral of the 0 function. That's one of the properties of integration. It's equal to 0. Okay, so because it's equal to 0, the integral of 0 between 0 and plus infinity. So when x is not different from 0, what's happening? When x is not equal to 0, sorry, what's happening? We can calculate actually this integral. We can do the calculation. We see that actually it's exactly the derivative, this inner function is exactly the derivative of exponential minus xt. If you differentiate this with respect to our integration variable t, the t is our integration variable, so let me just remind that. If we integrate with respect to this integration variable, this is the primitive we get, and we can calculate this. For x positive, sorry, I should make x positive. I should maybe have said that. If x is negative, that's not going to converge, but if x is positive, that's indeed converging. And in that case, I will have that e minus xt when t tends to infinity, that's 0, minus the value when t is equal to 0, so minus, that makes a plus, exponential minus x fois 0, so that's exponential of 0, that's 1. So that's equal to 1. So what is surprising here is that I've got a function, f of x, which is absolutely correctly defined, which is equal to 1 if x is strictly greater than 0, and 0 if x is equal to 0. What is surprising is that, well, this is not continuous, although everything here seems continuous. I'm doing the integration of a continuous function, so even the primitive should be even more continuous than the function inside. So that's pretty disturbing to see this kind of thing. So again, this is why we need to settle one for good, some conditions under which I will have, well, continuity of that parameter dependent integral on differentiability of it. All right. So this is the idea. What happens if your function is not regular enough is the limit of the integral of a sequence of function equal to the integral of the limit. That was our first example. Is the derivative of an integral depending on a parameter equal to the integral of the derivative, or continuous. That's the scheme kind of thing. So this is what Lebesgue integral is trying to do. to answer this kind of thing. And the main idea to Lebesgue integral is that actually that for regularity conditions and for many other things, we need not we don't need things to be happening everywhere. We need to that regularity at least is happening almost everywhere. So that's the idea that we're going to see, and that means, what does it mean to happen almost everywhere? It means everywhere except maybe on some places where it could be considered negligible. And so what we want to see is to have a good idea of what negligible is. Okay, here we've got a bad expression of negligibility, because for here you've got something, we have a bug in the code and it's a very 0.0000 value. And how bad it is? Well, it looks very small, but actually this can have some big consequences. Okay, so we need to have a fine idea of what is negligible or not, and for in order to do this, we need measure theory.